Okay, before we start, can I just confirm that you guys can hear me, see me, and see my screen? And that everything is working as well as YouTube. Please confirm with me. Cool, perfect. Great. Okay. Thank you so much. Okay, then we can start. Okay, assalamu alaikum and good morning to everyone. Welcome back to grade 12 Maths by Inspired Teens, where in today's lesson we'll be continuing sequences and series. Okay, hopefully we can finish it up today. Okay, please do remember, if you guys do have any questions, if you're new joining us, you can use the chat, you can use the Q&A, or you can alternatively, if you're on YouTube, you can of course ask on YouTube. All the documents, all the notes that I do with you guys will be uploaded to the Google Drive. Cool. Okay. So I believe last time we ended on arithmetic series. So we basically went through the proof, right? We went through the proof and we just discussed how it works. Okay, just to understand it. And yeah, it was pretty simple. Okay, let's just revise the definitions. So we have the general term for an arithmetic series. Remember, arithmetic is like a linear pattern, okay, where it has a common difference, okay, which differs to quadratic. Remember, quadratic has a second common difference, and of course differs to geometric, which has a constant ratio between each consecutive term, right? So constant ratio in geometric, it's more like multiplication, okay, where in this case, it's a difference. So we're adding or subtracting. Okay, so the general term for an arithmetic sequence is Tn is equal to a plus n minus 1 times the difference. Remember that is given in the formula sheet. And we have sum of the arithmetic series, Sn is equal to n over 2, open brackets 2a plus n minus 1 times d. So this is the sum. Okay. And yeah, we'll discuss sum now today. Last term, okay, so there's a formula with the last term as well for sum. N over 2 into a plus l, first term plus last term. So if we have the value of the last term, we can also calculate the sum, okay, of all the a certain amount of patterns in the sequence or series, right? So we're going to discuss sum in today's lesson. We're going to start off with that. So sum is basically if I have a pattern, right, arithmetic 2, 5, 8, 11, and so on. So remember, when I utilize this formula, right, we said that Tn is actually the value of the term, right? When we talk about value, it's actual like, so the first term. So in this case, the first term is 2. So this is Tn. This is the value of Tn. Tn is equal to 2. Okay. Actually, Tn, the n is the, remember we said the n is the term number. So we can describe this as T1 because the n is 1, it's term number 1. We can describe this as T2 because the n is 2, it's term number 2, T3 and T4 and so on. And again, yeah, n is 1, n is 2, and n is 3 and so on, right? So that's how we can discuss it. Okay, so yes, in that case, so that's Tn. When we talk about Sn, it's basically we are summing, we are adding up a certain amount of terms. So in this case, right, the value of T4 is 11, but the value of S4 would basically be T1 plus T2 plus T3 plus T4. It's adding up the first 4 terms. Okay, so that's what the formula helps us to do. So let's look at this. It says determine the sum of the following. The first 25 terms, they want us to calculate the first 25 terms of this pattern. Okay, so again, of course, we know it's linear arithmetic because we're doing that, but in the exam, they don't need to specify that it's linear or arithmetic because, of course, you need to calculate that. So in this case, I can see, is there a first difference? Is there a second difference? Is there a ratio? So between the difference between the first and the second terms, 18 and 13, it's important to notice, are we adding or subtracting? We are actually subtracting 5. Then we notice then from 13 to 8, we subtract another 5. So clearly this has a first common difference. If we had to just quickly calculate the next term, it would be 3 subtracting 5. Okay, so We know it's arithmetic. We need to calculate S25. Remember, Sn is here. N over 2 into 2a plus n minus 1 times d. N over 2, this is given in the formula sheet, 2a plus n minus 1 times that difference. So I want to calculate S25. Why? Because they tell me calculate the sum of the first 25 terms. So 25 is the number of terms. My first term is 18. So I sub it in there. N minus 1, n is 25 because I'm calculating for 25 terms. My difference, please do not forget the negative, is minus 5. So S25 is equal to 25 over 2, 36 plus 24 times minus 5 is actually going to be minus 120. Okay. Obviously, I think you just put that in your calculator one shot and you'll get the answer. 36 minus 120, that's going to give us minus 84 multiplied by 25 over 2. And we get an answer of the first 25 terms. For those who are doing it along with me, just confirm that this is the correct answer. But when we add up the first 25 terms, essentially we get negative 1050. Okay, basic sum example. Let us move on. Okay, so they want us to determine the sum of the following series. We don't have to do this example. The difference, okay, is 3. The difference is 3. Here we have the last term. Okay, we'll do it because we can make use of that last term formula. So here we can see arithmetic firstly, constant first, difference. Let's make use of that last formula. Sn is equal to n over 2, open brackets, a plus l. Okay. We want to actually calculate S25. So the reason we can use either formula, right? Remember, we can use either formula. You can use this formula. However, you cannot use this formula if you don't have the last term. And we have the last term here because of the dot, dot, dot. And normally they end it in a full stop as well. That tells you, okay, that's the end of the pattern. N over 2, 25 over 2. Okay, we actually don't know it's 25. Sorry. They don't tell us to calculate the sum of the first 25. They just tell us, that was from the previous question. They just tell us the sum of the following. Okay, any ideas? Somebody tell me in chat, how are we going to get the total amount of terms in this pattern? How would we know that? How could we get the total number of terms in this pattern? General term equals the last term. Okay, I see one correct answer. Others are not so specific. Yes, it's definitely Tn firstly. Okay. It's the sum is not 35. The last term is value is 35. Get Tn and make it equal to 135. I think you may mean 35. Okay. So yes, that's the second correct answer. Is essentially we have to calculate Tn. That is the correct approach. Okay, so that's the correct formula we need to use. However, remember we said T1, T2, T3. So if this was just the pattern till T3, the value of the last n, basically the n for the last term is the amount of terms there are in the sequence always. So whatever this guy is, 35, whatever is the Tn of 35 is going to be the answer. Okay, that's going to tell us how many terms we have in this pattern. So Tn is equal to a plus n minus 1 times the difference, right? So now remember, in this case, we are solving for n. We want to know which term number is 35. We know the value. Tn is value. 35 is equal to a, which is 5, plus n minus 1. We are solving for n. The difference is 3. Let me just shortcut to get the answer quickly so we can move on. Okay, so we actually get n as 11 when we do the simplification algebra. Okay, so n is 11. We know that, therefore, since this is T11, basically, since the last term is the 11th term, that means that there's 11 terms in the sequence. So S11 is equal to 11 over 2, first term 5 plus 35, which basically becomes 5.5 times 40, which is 220. So the sum of the first 11 terms or the entire sequence basically is 220. Okay, let's move on. The sixth term of arithmetic is 23, and the sum of the first six terms is 78. Determine the first. Okay, so I'm just gonna, we're not gonna do this example. You guys can practice this one on your own, but I'm just gonna do the basis of it. The sixth term of an arithmetic is 23. Okay, so just a hint. Remember, we've done multiple questions before, right, where we don't have all the information, and sometimes we, a lot of the times we've actually, either it's with X, then we solve using the difference. However, in this case, we could also use simultaneous equations, right? So don't be afraid to write out an equation, even if it has more than one variable, right? Remember, you writing it out, you seeing it written out, okay? It might give you a better indication of what you need to do in order to solve it, right? You might then realize that, oh, okay, I need to solve for A here and D there, and then you can work from there. So even if you're stuck, right, use the information in the written to at least write out something utilizing the formula for that specific section. So in this case, they say the sixth term, so I'm going to say linear because it is a linear pattern. The sixth term of an arithmetic sequence is 23. So T6 is equal to 23. And the sum of the first six terms, okay, so they're all for linear, it doesn't matter. However, okay, so then they say the sum, okay, the sum of the first six terms is 78. Sum, so S6 is equal to 78. Determine the sum of the first 21 terms. So remember, in order to calculate the sum of the first 21 terms, you're going to have to calculate S21. Okay. In order to calculate S21, n over 2, 2a plus n minus 1 times the difference. 21, you have, because it's 21, right? You don't have a, and you don't have your difference. So that's now what you need to solve for by utilizing this. So please have a look through these examples. They are exactly the same, just now we're using some as the previous examples that we've done. So if you're getting confused, go and rewatch how we did those previous simultaneous equations once, and then attempt this one. Let's move on to geometric series. Remember, we said sequences are the patterns. Series we describe as the sum of the patterns. Okay, let's discuss the proof, but first, before that, formulas. So remember the general term or general formula for geometric series. Tn is equal to a times r to the power of n minus 1, where r, let's start with a, or Tn actually. Tn is the value of our term, a is the first term, r is the constant ratio, basically what you're multiplying each term by. Could be a whole number, could be a fraction. N is the term number, and 1 is the number before 2. Okay, so sum of geometric series, two possible formulas. So we either use that or we either use this. Now you'll notice that they are extremely similar. Okay, what is the difference? So basically in this case, if you're going to have an r that is less than 1, who is calling me at this point in time? If you're going to have an r that is less than 1, you're going to use this formula. If you're going to have an r that is greater than 1, you should use this formula. Okay, that's basically it. And if we look at the differences, so let's just discuss it. Sn, sum of however many terms, is equal to first term, open brackets, 1 minus constant ratio to the power of the term number over 1 minus the constant ratio. And then this is just the other way around, Rn minus 1 and R minus 1 instead of 1 minus Rn and 1 minus R. In your formula sheet, for those of you curious, they only have the one on the right. Okay, so if I was you, I would just memorize the one on the left. So you know that the one on the right is given. I would memorize the fact that the one that's given in the formula sheet should always use when R is greater than 1. This one, you should always use when R is less than 1. Okay, so you just remember to swap it if your R is less than 1. Okay, so let's discuss the proof now, right? So let's look at the proof. Okay, so just remembering the formula, Sn is equal to that, right? So we're proving how did they come up with this formula? So firstly, we said that the sum of the first n terms, now remember, sum of the first n terms is just basically adding each term up. So when we look here, we are talking about T1, which is A, right? It is A, first term, right? What did they do to T2 to get T2? They multiplied it by R. R is the constant ratio. So remember, like, for example, let's look at our thingy proof, right? This is for arithmetic. Keep that in mind, right? A is first term. How do I get the second term? I basically add the difference. Okay, I add the difference. So I say A plus D. Okay. However, if I'm looking at geometric, remember it's a constant ratio, so I'm multiplying. So how do I get the second term? I say A times R. I multiplied by that constant ratio. How do I get the third term? I say A times R, which is the second term, times R again, and then again to get the next term. So that's why I get A times R, the second term, times R again, I get AR squared. How do I get T4? I take T3 and I multiply it by R. So AR squared times R. That's how I'm getting to the power of 3. Okay, and so on and so forth. And then what you do is you express the last few terms. Okay, so now how are we getting this last term? Again, we're making use of our general formula. Okay, what is our general formula? Tn is equal to A times R to the n minus 1. Okay, so for the last term, right, we're considering n as what? N is the number of terms, the total number of terms in the pattern, whether there's 55 terms, whether there's 65 terms, right? We're considering n as the total number of terms in the pattern. So basically the last term you represent by the formula, A times R to the n minus 1. So if there were 50 terms in this pattern, n is going to be 50, right? Remember, similar to how the arithmetic one works. Now, how do we get the previous one? N minus 2, because it's one term less, one term before. Okay, so the last term, we call this Tn, and then this is what? Tn minus 1. Why? Because it's, if this was 50, this would be the 49th term. Okay, again, if it's not that, it could work for any pattern, right? Regardless. So yes, that's how we get that. So A to the R minus 1, A to the R to the n minus 2. Okay. Thereafter, we multiply R by Sn. Again, you don't need to know why. You just need to know that that's how they proved it. Okay. We are not here to prove the geometric series proof. Okay. We're just here to learn it and put it in the exam if they ask. Okay. So the next step, so your first step is that just write out Sn with each term and write out the last few terms. Thereafter, you take Sn and you multiply it by R. So what happens when you multiply Sn by R? Each term basically, so T1, okay, I'll tell you why it's shifted in a bit. T1, or like why we didn't start here. T1 is basically A, okay, of course, it's always A, but now we are multiplying each term by R. We are multiplying each term by R. So that's why I'm getting as my first term as A times R. Okay, so just keep that in mind. We are just multiplying every single term by R. So if we had to do it there, that would be R, an extra R, an extra R, and so on and so forth, right? So that's exactly what we are doing. So T2, we're just getting the first term, but we're multiplying each one by R. Then T2, of course, is going to be R and R again, and then T3, and so on and so forth. When we look at the end, right, we basically get R to the n minus 1 times R to the 1. Okay, I'll explain that now. Okay, so yes, when we look at the end, right? So again, we're multiplying every single term by R. So we're basically taking the top pattern and multiplying everything by R. So when we do the last term in the pattern, remember the last term was A times R to the n minus 1. For this second set of sum, what are they doing? They are multiplying all by R. Okay, so now remember, we basically have A times R to the n minus 1 times R. Okay, it's multiplication. So here we have common bases. Remember, this is R to the 1. When you have common bases, you simply add the numerators. So A times R to the n minus 1 plus 1. Minus 1 and minus 1 are going to cancel each other out. You are left with A times R to the n. So if you're wondering, how did we get the last term as A times R to the n? That's how we got it. Okay, because we're multiplying everything by n in the second line. And then we get the previous term, A times R to the n minus 1, and so on and so forth. So the reason that it is aligned the way it is because the second pattern here matches the first pattern. The second pattern matches the first pattern. Okay, so that's why it is aligned like that, because you can see that, hey, these are all the same. Okay, what's extra and not part of the same thingy? A and A times R to the n. Those are different. They don't have anything common. They're not common between the two. All right. Okay, so therefore, then what they do in order to continue this proof is they take the first one, number 1, and they take number 2, and they subtract number 2 from number 1. So Sn minus R times Sn. So when we subtract them, remember, AR is going to cancel AR because we're subtracting it. That's going to cancel. That's going to cancel. That's going to cancel. That's going to cancel. They're all going to cancel eventually because we are subtracting top one minus bottom one. Right. So in that case, just say minus. In that case, we will be left with A times R to the n and A. So that's what we're left with. A minus A times R to the n. Because remember, this is originally plus, but we subtracted, and that will change to a minus. Okay, now we are actually getting somewhere. If we look at this, we have Sn minus R times Sn is equal to A minus A times R to the n. Here we can take a common bracket of Sn. Again, I know it's weird things that are, not used to, but I'm just here. I'm hoping you get the gist of what's going on, right? And then you need to memorize this proof. Wait to when it comes out, if not when. Okay, so Sn, when you take the common factor, you're left with 1 minus R. So now you actually have Sn alone, right? And then on this side, you take a common factor of A. Then you leave Sn alone by dividing both sides by 1 minus R. Cancels, and of course, then you're left with this formula for the sum. A open brackets 1 minus R to the n divided by 1 minus R. Let us move on. Proof. Right, so just remember, like maybe closer to the exam, you can rewatch this video one more time to revise the concept of the proof. Okay, let's do a question. Right, example 1, given the series -2, 6, -18, 54, determine the sum to 9 terms. So let's determine what type of pattern it is. First, -2, wait. Yeah, -2, I think there's just commas missing. 6, -18, and 54, and so on and so on. So let's try and calculate the difference. -2 plus -2 minus 6 is we're adding 8. To get from there to there, we're adding, subtracting actually, 24. Okay, so already doesn't make sense. How can a difference go from 8 to 24? Okay, let's see. Maybe it's quadratic. Yeah, we're adding 72, I think. Common difference is not, there's not going to be a second common difference, definitely. Okay, again, so clearly they don't match up, right? So this is definitely not linear, this is definitely not arithmetic. This is therefore geometric, right? Upon inspection the first time, right, you should be able to determine whether it's quadratic or whatever. You can just use your calculator, see if there's a difference, see if there's a common second difference, if you're really stuck. In this case, now I try geometric. Let's see, again, how do I calculate geometric's difference? I say T2 over T1, which is equal to 6 over -2, which is equal to -3. You can confirm that by saying T3 over T2, which is going to be equal to -18 over 6, which is equal to -3. Okay, so now it's starting to make sense. X is 3. Okay, yes, correct. Right. Well done, right? So yes, like I said, upon inspection the first time, you should be able to determine whether it's one of the 3 different types of pattern. Let's look at A. They want the sum to 9 terms. So we have R. Okay, we have A. Let's do the sum. So S9, right? Remember which formula we need to use. In this case, let's look at the criteria. If R is less than 1, we use a certain formula. If R is greater than 1, we use a certain formula. This is definitely, does a negative matter? Yeah, R is less than 1, so we utilize this formula. So it's the formula that's given, we basically swap it around. S9 is equal to, okay, let's write it as Sn. The formula is equal to A 1 minus R to the n divided by 1 minus R. So now if I want to calculate S9, okay, A I have as -2. 1 minus what is R? We said R is -3. -3 to the power of n, which is 9, because I want to calculate the sum of the first 9 terms, minus 1, sorry, divided by 1, minus 3. You put all of this into your calculator, and you're going to get an answer that the first sum of the first 9 terms is actually -8. Sorry, -9,842. Okay, for those of you who are doing this with me, please confirm that that is the correct answer. Let's look at B. Okay, so I hope that makes sense. The value of n, if the sum of the series is -797,162. So let's try and understand what they're asking for, what they're giving. The value of n, okay, so what n are we talking about, right? Let's see. They say the sum of the series. If they say the sum of the series, that means the entire series. When they add up the entire series, okay, they get -797,162. So we have the answer to the sum of the entire series, and they basically want to know the n, which is n of course, the last term, or basically the amount of terms that they are in this sequence. So firstly, don't be scared, it's backwards. Okay, I'm dealing with a geometric sequence. I do not know what to do. I'm confused because it's given backwards. They're giving me the sum of the series and they want n. However, I do know a formula, right? Of sum. I know that Sn is equal to A, open brackets, 1 minus R to the n divided by 1 minus R. Okay, I know that A is -2, 1 minus, I know that R is -3. I know that I'm calculating n because they want us to find the value of n. All right, and then 1 minus -3. Okay, so now in this case, I have one unknown, so I cannot have another unknown here to say Sn or n, because I need to know the number of terms. That's where this guy comes in, because I know the value, Sn is also the value of the sum of a certain amount of terms, which I want to calculate how many terms am I summing to get -797,162, basically the total amount of terms in the sequence. So then I equate it to this value that was given. Okay, let us do the simplification. Okay, here I get 1 minus -3, I get 4. All right, because you add it. So I'm going to multiply this guy by 4 and divide it by negative. Okay, let's take it step by step, right? Let's take this over as a multiplication. Because it's division on the right, I'm going to take it over as multiplication. I get -3,188,648. That's quick maths. Definitely did that in my brain. Okay, is equal to -2. Okay, 1 minus -3 to the power of n. Okay, we can't take this negative and negative and make it a positive because of that exponent, right? Let's sort out. You have to sort out the exponent first. Okay, now I take this value over the -2. It's multiplication on the right. I take it as division over to the left hand side. Negative, negative, divide. You're going to get a positive, and you get 1,594,324. Okay, equate this to, I can get rid of my brackets, 1 minus -3 to the power of n. Take the 1 over as minus. Yes, you get 1,594,323. Okay, and you left with -3 to the 9. Okay, 2 ways you could opt to solve this. Okay, I don't know if you guys remember the shift fact method that I told you guys about, but basically if you want to write something as its exponent, as its simplest exponent, you can put it in your calculator. So I'm going to put, so okay, before we get there, let's discuss the unknown, right? So the unknown is in a weird location. The unknown is in the exponent. So utilizing, just from finance, which I'm guessing you guys haven't got to yet, but from finance from last year, you should have been solving log questions. Can I just get a confirmation that you guys have been solving log questions? Okay, while you guys are typing, I'll continue talking. Okay, so there's two ways to go about this. One is log. Okay, that's the first way. The second way is to actually just, because you have whenever you have an unknown in an exponent, you always want to express both sides of the equation with the same base. Same base. Whenever you have an unknown exponent, you want to write both sides of the equation at the same base. Okay, mixture of yes and no's. Okay, whenever you have an unknown base, you want to express both sides with the same exponent. So if it's an unknown exponent, same base. That's basically what you want to do. Okay, unknown base. Okay, you want to express both sides of the equation with the same exponent. Okay, I'm going to write that long story out now. Express okay. Very neat. Okay. So that's just a general rule. Okay, so in this case, yes, I see. Okay, unknown exponent. When I have an unknown exponent, I want to express both sides of the equation with the same base. So basically, I need to get it to a base of -3. Okay, so what you can do, let me just think. Okay, so what you can do actually, because here it's -3, not +3, you want to take over your negative, okay, divide it by negative. So you're left with -594,323, which is equal to still -3 to the power of n. So in our calculators, 1594323 equals shift fact. Okay, we're gonna get an error. Yes, very good. So we're going to put the positive value 1594323 into our calculator. You're going to press equals. Okay, you're going to press shift, which is on the top left. And if you look for fact, remember we said it's on the third row. What is that? ABS, then it's fraction, then it's like a brackets with a dash inside, and then to the right of that we have basically this. And above it, it says fact. It's a button on your calculator. So you press equals to shift fact and shift fact. Okay, and it basically gives us 159,432 as 3 to the 13. So just this value as 3 to the 13. No problem, you may leave and catch up later. And the negative multiplies become +3. Okay, so yes, we get 3 to the 13. So remember, -3 to the 13, either way is going to give you a negative answer. Why? Because it's an odd number. Remember we discussed, I believe we discussed it with, I discussed it with your class. Whenever you have an exponent that's even, you're going to get the positive value no matter what, even if the answer is negative. Whenever you have an exponent that is odd, that's when you're actually going to get your negative answer if the base is negative. However, in this case, you could just even use brackets where this 1594323 is going to give you 3 to the 13 and then multiply it by -1. You get that and you're left with -3 to the n. Okay, so even here you could consider both bases -3. Both multiplied by a -1, so they could even cancel, or you can consider both bases -3. It doesn't really matter. Okay, and then you get 13 is equal to n. Okay, because why? Because when your bases are the same, you cancel them, you drop your bases when they're the same. So basically n is equal to 13. I even forgot what question we're doing, but yes, to solve this equation, which is basically the value of n if the sum of the series is negative 7972. So basically we have the sum of everything. We use the sum formula, work backwards to calculate, okay, when we sum up everything, how many terms did we actually sum up? We added together 13 terms to get that. But it's a negative, so would it be a fraction? I don't understand. By what do you mean, would it be a fraction? Okay, so that's a basic example of a decently-ish hard example of how would you write it video log. Thanks for reminding me. 35, okay, cool. Okay, so what is this? Geometric. Let us do log quickly. We're going to learn that base exponent equals to answer. Okay, so this is just an expression for n exponential equation, basically, right? You have a base, you have an exponent to that base, you're going to get an answer. Okay, why are we expressing it like this? Because when we want to do its inverse, basically, you're going to utilize log. Okay, whenever you have an unknown exponent, when the exponent contains a variable, and you need to, because remember, when we're solving for variables, we always want to isolate the variable, meaning we always want to leave the variable alone. We want to leave it on its own. So if you want to take that variable out of the exponent and leave it on its own and then express something else, that's when we're going to use log. So when we have something like this, for example, in what case would we use it? If we had a to the power of x is equal to q, right? So we're going to do it in terms of both. Now, let us talk about it. Sorry, just 1 second. You just the cat. Yes, Astro. What's up? I'm teaching. I cannot give you attention. Okay, so yes, for example, okay, let's rather maybe, okay, let's not give it values. Okay, let's just say, denote that this is our unknown. We're solving for x. Okay, so we're going to do it in terms of both. Okay, so firstly, because your exponent is your unknown and you want to isolate your exponent is the first thing you write. Okay, your exponent is going to be alone and it's going to be equal to. What is it going to be equal to exactly? It is going to be equal to log. Okay, so we put in log. So again, when do we utilize this? We utilize this when we have an unknown exponent. So as you can see, log puts our exponent alone on itself. So clearly, in my first step, I've already put my exponent alone on its own, right? So I have log, and then I keep the base of log the same. So remember, log has a base as well. If you look on your calculator, top right, just underneath the switch on button, you'll see log. Okay, I keep the base the same. I have log base, and I put my answer on top of my log. So this is how I like to remember it. Base exponent gives me answer. Exponent is equal to log base answer. All right. And just remember, you keep the base the same. Your exponent is your unknown. So that needs to be alone naturally. And then the last thing that you can't remember, maybe the answer. Okay, that goes in the space that's left over after I know exponent alone, base is base. Oh, answer. Okay. So in this specific example, how would we have it? We would have x alone, because our exponent is our unknown, log, what is the base of x? A Q. Okay, simple as that. So in this case, let us go to the step -1594323 is equal to -3 to the power of n. Our negatives cancel on both sides. And now we have an unknown in an exponent. We shall use log. Okay, so unknown in an exponent. Remember, I have base, exponent gives me answer. So I'm going to say exponent is equal to log base 3 answer 1, 5, 9, 4, 3, 2, 3. I put that in my calculator. 1594, 323, and I get n is equal to 13. Cool, let's move on. Will they ever give us an unknown base or an exponent? They could potentially. They definitely could potentially. Let's have a look at sum to infinity, which is to do with geometric sequence. Okay. Okay, don't worry about the thus thing. It is a proof that is not important to us. However, what we need to know is that only a geometric series with r being between -1 and 1, okay, and r cannot be equal to 0, will have a sum to infinity. As sum to infinity will approach a set value. This is known as a convergent series. So what is a convergent series? A convergent series is basically a series where r is greater than -1 or less than 1. Or we describe it as a series that converges. What is a series that converges? A series that converges is a series where r is between -1 and 1. We have a sum to infinity. So sum to infinity is a calculation that, how would you write it? Oh, sorry, I read that already. A sum to infinity is a formula that calculates when we add this series forever and ever and ever and ever, we utilize this formula. Okay, so the sum to infinity formula, which we are going to use as yet, they say the question is, for which values of k will this series converge? So they want to know, when is the series going to converge? Okay, so firstly, a series only converges when r is between 1 and -1. That's when a series is going to converge. So they want to know for which values of k will the series converge. So we need to calculate what r, what does it, how do I phrase this? Which series will it converge? So basically we need to place r inside of here, okay, and then solve accordingly. So in this case, we have our terms t1, t2, t3 in terms of variables. So we calculate r and we're going to input it there, right? So let's first calculate r. Remember, r is t2 over t1. Okay, the fact that this has converged, right, and asking us for which value of k will the series converge, that automatically tells us geometric. So we know it has r. T2 is 8 into k minus 2 squared divided by 4 over k minus 2. Now I can simplify. One of the k minus 2's on top cancels with the bottom k minus 2. I simplify 8 and 4. At the bottom, I get 1. On top, I have 2. I am left with 2, open brackets, k minus 2. So basically, I have r now in terms of, I have r in terms of k. Okay, so what do I do? If I want to know the values of k for which this series will converge, remember, r needs to be in between these two. So in order for the series to converge, 2 minus k minus 2 into open brackets k minus 2 needs to be greater than -1, but less than 1. Okay, so now I can calculate the values for k in which the series will converge. So this is inequalities. So how do I solve dual inequalities with an unknown in the middle? I basically would solve it how I normally do, by taking it over to the other side. Just here, I have two sides to take it over. So this 2, I have to take it over to both sides. So firstly, this 2 is a multiplication. So I take it over as division. So I say -1 over 2. And I say 1 over 2. So I divide both sides by 2. Thereafter, I take the 2, this positive 2, sorry, over as addition. So I say k, a half plus 2 is 2,5, which is 5 over 2. And a half, -1/2 plus 2 is going to be 2. No, 1.5, which is 3/2. Okay, the signs are not going to switch. Let's clarify this misconception. The signs are not going to switch. In inequalities, when is the sign going to switch? When you divide or multiply by a negative. When you divide or multiply by a negative. The only times you swap your inequalities, like turn them around, like maybe it would be like that, is when you divide or multiply by a negative. What will happen to the signs if the middle variable was a fraction? Nothing. You just solve like how you would solve normally. If you again, if you're dividing or multiplying by a negative, that's when it's affecting your signs, nothing else. Any other division or multiplication is not going to affect your signs. Okay, let's move on to sigma notation. So that was series converge. Actually, what is this? Sum to infinity. Okay, let's do this example before we do continue. Okay, it is a sum to infinity example. So it's not a basic example. Okay, but at this point, I expect our basics to be decent, right? This is like monotonous at this point. We've done like 7 or some odd formulas, okay, of geometric, quadratic, linear. And we know basically how each formula works, right? Especially when you with regards to Tn, with regards to, okay, we can't do this until we do sigma, so we can do sigma, then we can do this. That's fine. Or can we? Let me get a basic question for this, and then we can do sigma. Okay, so we have a pattern. They say consider 1, a half, a quarter, and 1/8. They say calculate S infinity. Okay, so in this case, firstly, we know that S infinity is equal to A, open brackets. Okay, we have 2 formulas. Let's first calculate R to know which formula we want to use. So remember, R is equal to T2 over T1. So T2 is a half over 1, which basically tells us that R is a half. So it's multiplying by a half each time. So here we can see that R is actually less than 1. Okay, because it's a half. So we have Sn, this guy, right? Sn is equal to A, open brackets, 1 minus R to the n over 1 minus R divided by 1 minus R. Okay, so in this case, let's consider our unknowns. They want us to calculate S infinity. Our unknowns are A and our unknowns are R. Sorry, this is the wrong formula. Our formula for sum to infinity is basic. Our formula for sum to infinity is right here. It's A over 1 minus R, simple. Okay. Astro? A over 1 minus R, quite simple. So again, our unknowns here are A and R, which we've solved for easily. They want us to solve for S to infinity. So I need to know A. A is 1 divided by 1 minus R, which is 1 minus a half. Therefore, I can calculate that the sum to infinity is actually 1 minus a half, sorry, 1 divided by 1 over 2. For those of you calculating this with me, please confirm with me that the answer is 2. So the sum to infinity is 2. So just a basic example of utilizing that formula. Let's move on to sigma notation. Perfect. Okay, sigma notation is denoted by this symbol. Okay, sorry, just give me 1 second. I will be back in one. Okay, I lied. That was 15 seconds, but I'm back, right? So sigma notation is denoted by that symbol, which means the sum of. Okay, so whenever you think of the word sigma, you need to think of sum of. Whenever you think of the symbol, you need to think of sum of, right? If you do physics, if you remember in momentum, we considered conservation of linear momentum, the sum of the momentum before, and sum of momentum afterwards, and we use that same symbol, okay? So let's look at the format. So we have our sigma, right? Then on top, we actually have the end term and the start term. So basically, these are in terms of n, right? What is our start term? Is it the 5th term? Is it the 6th term, right? What's our end term? Is it the 27th term? Is it the 4th term? Or whatever term is our end term, right? Then we have the sigma denoted there. And then we have the formula of the series, which is Tn, very important. So it looks something like this. So the value here is the start term, the value of n for the start term, the value of n for the end term. It's just represented by r as any value. And then we write Tn right next to the sigma. Okay, so this is important. We'll go through that in a second. Okay, find the first 3 terms to check if arithmetic or geometric. Okay, we'll go through the steps as well. So let's look at this example and let's learn through this example. Okay, so firstly, we have this, right? Sigma, n is equal to 3 at the bottom, 7 on top, and 2n. Okay, so let's distinguish. Remember, this is our last term. So not the value of the last term, it is n for the last term. The last term of this pattern, n, it's n, right? So it's the 7th term basically is what we're talking about, right? This is 3rd. So actually the first pattern in our pattern is we're starting off with the 3rd pattern, technically. It doesn't really matter, right? You'll see now it doesn't really make a difference. But this guy is actually our first term, the first n that we're going to work with in the specific pattern. And then, of course, this is Tn. This is the formula that calculates the pattern, right? Remember, we're dealing with the sum. They're giving us Tn, right? So this is just 2n, okay? This is clearly linear, actually. So, okay, as they explain it there. Right, now, how do we calculate the number of terms in a pattern? Calculate, hashtag means number, the number of terms in the pattern. So we want to know, okay, I know we're working with the 3rd term first and then the 7th term last. So basically we're working with the 3rd, the 4th, the 5th, the 6th, and the 7th. Okay, so in this case, it's easy. You can count that there's 5 terms. However, if it's like to say this is 7,321 and this is 982, then you're not going to count from 982 to 7,381. You're going to use this. You're going to say n term minus start term plus 1. N term minus start term plus 1. So the number of terms. Okay, and why do we need to know the number of terms before we calculate it? Because, okay, let's just calculate first. Number of terms in this pattern is going to be equal to what? The n term, which is 7, minus the start term, which is 3, and we are going to add 1 to it. So it's basically 5. So we now know that there are 5 terms in this pattern. Please, it's not just n term minus last term. Don't think that there's 4 patterns in here. 4 terms in that pattern, because you need to calculate, you need to include the first and the last term. Okay, so 3, 4, 5, 6, and 7. Okay, normally when you calculate, you just start from 4, 5, 6, 7. That's why you're getting 4. But however, you need to always say n term minus first term plus 1. So why is it important for us to know the amount of terms in the pattern? Because this is sigma. So sometimes they'll literally give you this and they'll say evaluate this. So they're telling you sigma starting at 3, ending at 7, Tn. That is telling you calculate the sum. This means calculate the sum of these terms and here's Tn. That's what they're telling you. Sigma, if you're given sigma, it's sum. So this here, okay, is Sn. This entire thing represents Sn. So Sn is equal to this is arithmetic. So n over 2, 2a plus n minus 1 times the difference. Okay, the entire thing is Sn. Okay, so we need to know how many terms are we summing. That's what this helps for. Okay, we are summing 5 terms. It's equal to 5 over 2 into 2 into what's our first term. Okay, sorry, I forgot rule number 1. Okay, so firstly, whenever you're dealing with sigma, right, always calculate your first 5 terms in the pattern. Always. Whenever you're dealing with, not first 5, sorry, first 3. Whenever you're dealing with sigma, you need to calculate the first 3 terms in the pattern. How can you do that? Because you have Tn. So Tn is equal to 2n. And remember, n, my first n I need to use is 3, because they say 3, not 1, 3. So 2 into 3, which is 6. And for the second term that we're going to be working with, I'm going to use n is equal to 4, because it goes 3, 4, 5, 6, 7. So 2 into 4, which is 8. Then 2 into 5, which is 10. Now I can calculate difference as well. T2 minus T1, which is equal to 8 minus 6, which is equal to positive 2. Okay, so the first term that I'm working with, I calculated as 6 plus n, which is 5 minus 1, times the difference I worked out as 2. So when I do this calculation, I get the sum of the first 5 terms as 50, I believe. For those of you who are doing it with me, just confirm that that is correct. Okay, what you could also do is calculate the value of the last term, which you're going to substitute n as 7, and then use that Sn formula with a plus L, if you'd like to use the last term. Okay, but I'm pretty sure it is correct. Okay, so let's end it there. Next week, we'll continue with just basically like 1 or 2 examples, and then we're going to move on to what is next? Trigonometry, I believe. I think, no, let me see quickly. No, functions, sorry. Just quickly before we do leave, tell me, what are you guys busy with in school? They got already, okay. Inverse functions, perfect. Okay, trig, circle, geometry, functions, and trig, ending functions. Yeah, most of these should be ending functions. Get towards the end, inverse functions. Euclidean, trig. Okay, cool. So we again somewhere in the middle of everyone. Okay, but yes, for those of you, okay, so everyone should join. Please join the later on class. Okay, where we can go through. We're gonna host the second class for free, a free trial, just for you guys to get a feeling of what the class is going to be about. Okay, cool. But thank you guys so much for joining. I will see you guys next week. Have a good week at school. Jazakallah khair. Thank you. Assalamu alaikum and goodbye.